Hello everyone, welcome to the 22nd lecture, second part of 22nd lecture on NPTEL course on scalable data science. I am Professor Shourangshu Bhattacharya from Computer Science and Engineering at IIT Kharagpur, and today's lecture is going to be a continuation about the alternating direction method of multipliers or ADMM. So, in the first part of this lecture, we had looked at the distributed optimization problem, and we had looked at how we can pose this as a equality constraint problem, or rather equality constraint optimization problem. And then we had gone into the precursors of ADMM, or the methods that led to ADMM, which are basically methods of solving equality constraint optimization problems. So, we have seen the dual ascent method, and we have seen that the dual ascent method has a problem of if the Lagrangian is not strictly convex, that is, if it does not have a unique optimum, then the solution can oscillate. To solve that problem, there is the method of multipliers method, which basically uses a augmented Lagrangian instead of regular Lagrangian, which basically is always strictly convex. And then finally, we have seen that this has a decomposition problem because we use the augmented Lagrangian. So, the method, the objective does not directly decompose, which leads to the method of ADMM. So, just to recall the ADMM, this is the problem formulation. So, we are using the simplified problem formulation where you have just for simplicity sum of two functions f and g, and these are optimized with respect to x and z, subject to this kind of an equality constraint. So, here we use a general equality constraint. We will see in a minute for the specific constraint where x is equal to z, okay, which corresponds to the distributed optimization problem. Okay. And then we have already defined the augmented Lagrangian like this, and we see that because of this term, this squared term, this actually does not decompose into the form some let us say f1 of x plus f2 of z. So, this is what we would ideally want, but it does not happen. But nonetheless, we are so the ADMM method can circumvent this by using these three steps. So, in the first steps, actually here the problems are actually decomposing. So, in the first step you only minimize with respect to x, keeping the z and the y same for the previous iterate, then you minimize with respect to z, and then finally you minimize with respect to y. Okay. And if you do this, then as you can understand, you can do the first one in a different machine, the second one in a different machine, and then finally maybe the third one in a centralized machine. So, that is our strategy for distributed optimization. Now, the question is, so how did we arrive at this? Okay. So, yeah, so basically we see that the yeah, so we have seen that since we split the joint x z minimization problem, now the solution can be decomposed. Okay. So, earlier if we were not using ADMM, the first step of our solution would be something like we would have to combine these two steps into saying that x k plus 1 comma z k plus 1 is equal to arg max over jointly x and z, and then we would have to say something like L rho of x comma z comma y k. So, this would be the method of multiplier solution. Okay. Instead, we can now split it in the ADMM step. Okay. So, now why does this basically work? So, first some of the simple things. So, for this problem to have an or rather for a given solution to be optimal, that is optimality conditions. Okay. So, there are three optimality conditions now, because there are three variables. So, one is the primal feasibility, which is basically corresponding to gradient of L rho with respect to with respect to the dual variable, which is in our case y. Okay. So, x z y. Okay. This should be equal to 0. So, this is the primal feasibility condition, which also boils down to saying that your constraint should be satisfied. Okay. Then there are two dual feasibility conditions. Okay. One, when we differentiate with respect to each of the primal variables. So, when we differentiate with respect to x, L rho of x, z and y is equal to 0, and once when we differentiate with respect to z. Okay. So, these are the three optimality conditions. Okay. Now, as we have seen earlier, since zk minimizes this quantity, okay, if we set the gradient of, so if we set the gradient with respect to z and we put x k plus 1 and y k equal to 0, we get this condition. So, this is equal to 0, and now if we just substitute back the update for the y, if you recall, the update for the y k plus 1 is nothing but your y k and then plus rho times a x k plus 1 plus b z k plus 1 minus c. Okay. So, if you recall, this is your update for the y k plus 1, okay. And now you can see that it automatically satisfies the one of the dual feasibility conditions, which is this one. Okay. So, your z k plus 1 automatically satisfies the second dual feasibility condition. This we saw in case of method of multipliers also, just by virtue of using rho as the step size. Okay. So, basically we are left with these two unsatisfied dual feasibility conditions. Okay. Or not dual feasibility, but these two unsatisfied conditions. So, this should be 0 and this should be 0. If these two conditions are satisfied, then we can say that we have already reached the optimum. So, these conditions are satisfied asymptotically. So, what do we mean by that? So, basically in order to monitor the satisfaction of these conditions, now we define the two residuals. The first one is the primal residual, which is basically trying to monitor the convergence of the rather the satisfaction of the primal feasibility condition, which is the derivative with respect to the dual variable should be 0, okay. And that is simply this value A x. We know that at optimality A x k plus B z k minus C should be 0, and if we take R k to be just this quantity, actually we should take it to be just norm of this quantity, okay, then it should be 0. So, if a vector is 0, its norm should also be 0, okay. And the second thing is basically we have to monitor the other condition, which is this one, okay. So, this is the first dual feasibility condition that we get, that is gradient of f x k plus 1 plus A transpose y k plus 1 should be equal to 0, okay. And we see that so if we just now impose the condition that x k plus 1 minimizes this quantity, okay, and if we take the gradient and equate it to 0, because x k plus 1 minimizes this. So, we get that this should be equal to 0, and just like rearranging previously, okay. So, if we do the rearrangement, so we get that gradient of f x k plus 1 plus A transpose y k plus rho transpose this whole quantity is equal to 0. Now, we put this term, we couple this with the second term. So, we couple the two together, and then we apply the same update here, and we see that this is basically the y k plus 1 update, okay. So, so we can see that your y k plus 1 update is basically your y k plus rho into yeah. So this is so this is your primal residual, which is R k plus 1, okay. If you recall, this is the update, and so this becomes y k plus 1, okay. And now this quantity is the quantity that you want to monitor, okay. So, this is nothing but just negative of this. So, this quantity is nothing but the negative of this quantity. So, basically monitoring this monitoring this second primal residual boils down to just monitoring the difference between z and zk, okay. We will see this more, but essentially what this tells us is that now this quantity rho into A transpose B, A and B are all given, and zk is the z variable value in the kth time point, and zk plus 1 is the z variable value in the k plus 1th time point. So, this is the new z, then this is the old z, and if you take the difference between the new z and the old z and then multiply by this constant is just known, okay. So, if this z minus zk, so if this is 0, okay, if this goes to 0, then this product will also go to 0. So, basically the other residual, monitoring the other residual is equivalent to monitoring that the between two successive iterations the z variable, which is the second primal variable, converges and does not basically change. Okay. So, this can be thought of as the dual residual. Okay. So, now okay. So, we will state now the theorem of convergence of ADMM. Okay. So, we have already shown the iterates. Now, suppose the function f is f and g are two functions, okay, and these are closed, proper and convex. So, many of the machine learning loss functions are of this type. Okay. If this is the case, and the second condition is that the augmented Lagrangian has a saddle point, that is you have the optimal solution x star, z star and y star, and you have the dual problem which is lower than the which is basically an upper bound. So, basically if this, so this is the convex direction, so and this is the concave direction. So, if there are two directions, okay, and in one direction at this point x star, z star, so this is the optimal point x star, z star and then y star. Okay. If you go in the x z direction, okay, you always go higher. So, if your x is, if you move from x star and z star, that is you move on this axis, you always go higher, and if you move in the y axis, you always go lower. So, this is basically in some sense the dual problem, and this is the primal problem for some given. So, the primal problem for some given dual variable value, and this is the dual problem for some given primal variable value. If this condition holds, and this condition holds for all convex optimization problems, if this is the case, then your algorithm, ADMM algorithm, is guaranteed to converge. That is the basically the claim. Okay. Okay. So, now in practice what will you do? So, how will you observe? Okay. So, we have defined the primal residual already. Okay. Of course, this is the objective function value of a given solution. Okay. So, this is the rather the primal objective at optimality. So, as the algorithm converges, so the previous result states that if those conditions are satisfied, that is if your functions are closed, proper and convex, and if the Lagrangian has a saddle point, that is with respect to the dual variable, the objective function value always decreases, and with respect to the primal variable values, the objective function value always increases. Then you have that there is convergence, that is the iterates will converge, but this result says what the convergence should be. So, it says that as your k tends to infinity, so as you iterate more and more, the the primal residual will go to 0. Okay. The dual residual, which is the Sk that we have defined, that will go to 0. So, recall that Sk is just defined as this rho A transpose B Zk minus Zk plus 1. Okay. The objective function value f x plus g z will converge towards the optimal objective function value, which is p star, okay, and the dual variable will converge towards the optimal dual variable. So, these are the convergence results of ADMM. Okay. So, then the question is, if this is the convergence, so how should, when should you stop iterating? So, the iterations that are given to you, when should you stop those iterations? And the prescription is that you define a small number epsilon prime, epsilon primal and epsilon dual. So, these are basically some tolerance values, because so just like for any convergence of any optimization values, they may not be exactly equal to 0. Okay. So, you show some tolerance values, and whenever the norm of your primal residual is less than the primal tolerance and the norm of your dual residual is less than the dual tolerance value, you can stop iterating further. Okay. So, this is the recipe for the convergence of, or for the stopping of the ADMM iterations. Okay. Now, we come to the main idea that if you now look at the, so if we go back to our ADMM, okay, you see that this is this entire thing is an optimization algorithm, but these two steps are themselves optimization problem. Okay. So, this is a typical case with the ADMM algorithm, that it is called a meta optimization algorithm. Okay. So, yeah. So, the X updates requires solving an optimization problem. Similarly, the Z update requires solving another optimization problem. Okay. But as we shall see, for most of the problems that we will be looking at, the Z update may have a closed form solution. So, even though it is an optimization problem, it may have a closed form solution. So, hence ADMM is a meta optimization algorithm. So, it is an optimization algorithm which uses other optimization algorithms as its components. If your f is separable, that is, if your f of x, the original function, if f is separable, then A is conformably block separable, that is, if your A transpose A is block diagonal, then the X update splits into n parallel updates for Xi. Okay. So, yeah. So, we will explain that with a example. So, we take the example of now the distributed optimization problem. So, if you remember, our objective was exactly of this form. Okay. So, our objective was that you had to minimize summation over I is equal to 1 to m loss function of I x. This was the total loss of x. Okay. Now, this was equivalent to saying you want to minimize summation over I is equal to 1 to m L I of x I subject to the constraint that all of these x i's are equal to z. Okay. So, this is what we have written here. Okay. And if you see, the augmented Lagrangian for this problem is something like this. Okay. So, here the x variable is basically split into n many x variables, and if that is the case, as we shall see, yeah. So, basically now the 3 steps of ADMM become something like this, that you have your x update being split into so n x updates. So, this is for I is equal to 1 to n. Okay. So, your x update is split into n x updates. Okay. Your z update, z is the consensus variable. Okay. So, z is the consensus variable. Okay. Your z update becomes something like this, which is a closed form solution. So, remember, in the general ADMM, this z was also supposed to be so this zk plus 1 was supposed to be an optimization problem, but it turns out that if you try to solve that optimization problem here, if you see this, if you try to so we can write here. So, your zk plus 1 was nothing but minimum over z, and then your L rho, and then your x k plus 1 z y k. Okay. And you see the way things are. Okay. Okay. So, if you minimize it like this with respect to z, you will get that you can see that it will just be this squared error, and this will be minimized when you get you just set z to be equal to this value. So, you can check this just by differentiating and equating it to 0. Okay. And y update is of course like this. Okay. So, this is your ADMM iteration, and actually you can further simplify this, because now what you can do is you can just substitute this z back to here. Okay. So, if you do that, okay, if you do this substitution, what you see is that your updates, so you can just so your y update just becomes something like this. So, what is your y update now? Your y update is whatever are the updated x values. Okay. If you take the average of those, if you take the average of updated x values, okay, and then if you take xi minus that and then rho and add that to yk, that is your y update. So, you have basically eliminated the z by substituting this zk plus 1 into all the updates. So, zk and zk plus 1 into all the updates. Okay. So, so you see that into the first you get this is equal to 0, and hence you get this update, and then finally when you substitute zk, which becomes equal to basically xk bar, and that you substitute here, you get the modified x updates. So, your z is basically nothing but x bar of k. Okay. So, your zk becomes equal to x bar of k, okay, where x bar of k is nothing but your 1 by n summation over I is equal to 1 to n x I k. Okay. So for this kind of a consensus optimization problem, okay, so for the consensus optimization problem, which is this problem, okay, which is this problem, the updates are something like this. Okay. So these are the final updates. Okay. And the final solution is going to be zk, which is nothing but x bar k. So the average of all the x's is the final solution that you will get for the original problem. And as you can see, this is very easily implemented in a distributed setting. So all you have to do is you have to store the yik in the central machines and x1k like this till xnk in the machines, and then for the first step you have to send all the xi's to the local to the local machines. So in the local machine it can compute x bar k, and then the x bar k can be sent back to individual machines. So from the central machine the individual machine gets x bar k, okay, and then you have all the information to compute this objective function, because you have the fi. So fi is on the ith machine, okay, and you have the yik. So yik also has to be sent, okay, but you have the yik and you have the x bar k, okay. So then you can just optimize with respect to xi to get xi k plus 1, and once you get xi k plus 1 here, you can send that to the central machine to compute the x bar k plus 1 in the central machine, and once you compute the x bar k plus 1 in the central machine, you can compute all the yi k plus 1 in the central machine, and that you can send back. So that completes the description of the algorithm. So we further describe, so how will you solve this or how will you use this technique to solve the distributed loss minimization problem. So this is our distributed loss minimization problem. So this is a general form of our distributed loss minimization problem. You have the loss function L, which is a decomposable function over these x's, okay, and rather which is a decomposable function, yeah, over x's, and you have the regularizer which is dependent only on x, okay. So basically this each part Li of ai xi bi is the loss on the ith machine. So this is the loss on the ith machine, and all of the xi's should be equal to z, okay. This is the constraint, so that xi is equal to xj. So all of them are equal to z. So this is the consensus constraint. So as we have already discussed, a little bit of arithmetic shows that this is your update equation for xi, okay. So basically this is the loss part, and your ui is what is called the scale dual variables, okay. So your ui is the scale dual variables, these are something like yi, okay, and then you can compute these as you can compute them using this formula, and then you can just update ui k plus 1, okay. And then this is the final solution. Okay. So, so this is a simple small toy problem which is taken from Stephen Boyd's slides. Okay. So basically let us say that this loss function is hinge loss, which is basically your L of u is nothing but 1 minus your 1 minus u, the positive of this is nothing but max over 1 minus u comma 0, okay. And you have capital N is equal to 400 and small n, which is the dimension. So, this is the dimension of u. So, dimension of u, okay. So, this is basically u's dimension, okay, and this is the number of examples. So, this is the number of examples, okay, and the examples are split into 20 groups, okay. So, so this is the scenario and this is the problem that we are solving, okay. So, you see how so each of these lines is the separator, or so this is a classification problem. There are two classes. You can see that your blue circles are points for class 1 and green crosses are points for class 2, and this is supposed to be your optimal solution, okay. But you have now 20 optimal solution, because you remember you have xi for each I, okay. So, and this dotted red lines are plotting the separating hyperplane. So, these are plotting the separating hyperplane for each machine I, okay. And this is the iteration 1. So, your k is equal to 1, okay. And now, as the iterations progress, so for example, after 5 iterations, you see that your hyperplanes have all come together a little bit. So, you remember that your so in this case basically your, if you recall, your primal residual is something like a x plus b minus c. So, in this case it will just be x minus z or x I minus z, okay. So, for each I your primal residual will be x I minus z, okay. And you can see that your this this black line corresponds to something like z, because your z is nothing but your x bar. So, your z k is something like x bar k, okay. And the question, so basically your residuals are how close are these lines to this black line, okay. And you see that they have become much more closer. So, your r k primal residual is actually going down, okay. And your dual residual is nothing but the difference between z k and z k plus 1. So, you see that as the iterations are progressing, your z k and z k plus 1 are roughly the same. So, your black line is the z, okay. So, roughly they are the same, and yeah. So, and now you see, so all the hyperplanes have converged to the black line, and the black line between two successive iterations have also become same. So, both these residuals, sorry, so both the residuals have become 0 or very close to 0 at iteration 40. Okay. So, this is how the algorithm progresses. Okay. So, with that we conclude our discussion of ADMM, and these are the references. So, the first one is the primary reference from where all the materials have been taken, and the second one is an application that we have explored for ADMM. Yeah, so the first one is the primary reference. Okay, thank you.